Hello, this is Greg Risterman from Olympus. I'd like to welcome everyone today to this webinar on total focusing method versus phased array, when to use each method. In this webinar, you will learn the difference between the TFM and the phased array UT. After this webinar, you should be comfortable making a decision on when to use one method over another. We will cover the advantages and limitations of each method and propose specific applications where TFM should be selected and others where PAUT should be chosen. Our presenter today is Stefan Kucher. Stefan is a global advanced product support specialist. He's worked at Olympus in product development and as a product specialist for 9 years. In 2017, he transitioned to work in the inspection world to gather more applicative knowledge with boots on the ground. In 2019, Stefan rejoined Olympus as a leader for global advanced product applications. Stefan is now supporting worldwide on applications, trainings, and industry projects, and as an ultrasonic advanced product specialist. This informational webinar has been scheduled for approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of the screen during the presentation. If we don't get to your questions during the live event, they will be addressed personally either by email or phone after the event. So now, without further ado, I'd like to turn the presentation over to Stefan. Stefan, you may take it away.
Thank you, Greg. Hello, everybody. Welcome to this session. As Greg mentioned, we're going to go over TFM and phased array. What are the differences between the two, when to choose one versus the other, and the other versus one. So, the agenda for today, we will start with a brief recap of what is a linear scan and what's a sectorial scan for phased array. And we'll also cover the differences between full matrix capture, or FMC, and total focusing method, or TFM. The topic of FMC and TFM methods, how they work, how they're set up, that's already been covered in the previous webinars, so we'll go fairly quickly over that. But you're more than welcome to view our previous sessions about that if you have any questions. We will then talk about signal characteristics. What are the differences between a phased array signal and a TFM signal? What advantages does TFM bring? What drawbacks as well? In terms of scan plan, what elements should we consider? Can we use any probe, any strategy, and the technology will just figure it out, or is there more to it than just beautiful images? Then we will talk about, of course, 0-degree inspection, angle beam inspection. How does TFM compare to phased array? How similar are they, and what separates them from each other from an application point of view? Then finally, we will wrap this session with a summary of what was discussed, and also a period of question. So first of all, phased array linear scan. A phased array linear scan, basically, you have focal laws generated over a series of elements using the same angle, and the A-scan density and coverage is defined by the element step resolution. So one aperture generating one focal law, then we move on to a different aperture generating another focal law with the same angle altogether. The advantages of a linear scan, so it produces the same results as conventional UT raster scan, so without the need of moving the probe in and out from the weld like so. It eases the calibration due to only producing one angle. The beam resolution also is the same regardless of sound path, as all focal laws are parallel. However, as you can see in this representation, coverage is pretty poor with only one angle in one group. So that leads to the need typically for multiple groups, and also long setups, long calibrations, and larger data files. For sectorial scan, the focal laws of different angles are generated using the same elements. So one fixed aperture generates multiple angles, and the density of the A-scan and coverage is defined by the range of angles from start to end, and also angle resolution or angle step, 1 degree, 2 degrees, 0.5 degree, and so on. An advantage of a sectorial scan is that you have a large covered area in the inspected part from a small footprint on the surface. The probe is in this example is quite big actually. Typically a smaller 16-element probe can cover half an inch V-weld with no problem in a single index position. Also, flow characterization is improved because of the multiple angles. Fewer focal laws are required to cover the weld area. However, as we go into longer sound paths, the beam-to-beam resolution gets worse as they're not parallel. They're actually moving away from each other, which also creates more difficult calibrations when we go into these longer sound paths. FMC, or full matrix capture, that is an acquisition strategy. So basically a single element is pulsed, and all of the probe's elements receive the reflected signal. That's done for the first probe element, and that's done for the rest of them, and the process repeats until each element of the array has fired and all transmit and receive combination has been acquired, and that's what we call the FMC raw A-scans. The TFM, or total focusing method, on the other hand, is an image reconstruction process that uses those elementary A-scans we just talked about. So the process requires key variable inputs such as acoustic propagation mode and resolution. Acoustic propagation mode, meaning are we going to use longitudinal waves, transverse waves, are we going to skip, mode convert, etc. And resolution being how fine or how coarse our grid of inspection is going to be. The resulting wave sets represent the path of the ultrasound beam from the transmitter to a specific position in the region of interest and back to the receiver according to the selected propagation mode. For example, with a 2T, we expect to pulse, hit something, and then receive. With a 4T, we expect to pulse, skip, hit something, come back, skip, and then go back into the probe. So why would we switch from phase array to TFM? Is it better than the other one? Is it more precise? As we'll see deeper in this session, it really depends on what you're trying to achieve and what are your priorities. Differences in signal, what to expect from TFM signal compared to phase array. First of all, TFM has the advantage of being focused everywhere, of course, provided that the setting enables operation in the near field. Past the near field region, focalization parameters have little to no effect on the measurement, just like with phase array. Generally speaking, though, many will agree that TFM can produce more appealing images, which is the driving force behind this technology. TFM performs better than phase array, also when it comes to reducing near-surface echoes for 0-degree inspection, and that is simply because of its firing sequence, where with FMC, you pulse one element at a time compared to phase array, which generates a wavefront from an aperture of elements. So less powerful ultrasound, less reflection from the interface. That being said, using a pitch catch phase array configuration, such as a DLA probe, for example, also helps in that issue with the near surface echoes. Another aspect where TFM excels is the reduction of geometrical echoes. And again, that is simply because the TFM natively is focused everywhere in the near field again, and that helps to reduce those unwanted echoes. If we put them side by side, here's an example of a phase array linear scan and the response of 1.5 millimeter side drill holes over a depth range of about 60 millimeters. The probe used in this example was a 5 megahertz, 0.6 millimeter pitch, and it was in direct contact with the block. The focus depth was set to 30 millimeters. So notice, as I told, that the near surface echo or main bang is quite big, and also, as we typically see with phase array, the deeper we go in the material, the resolution or the actual shape of the reflector and its amplitude starts to degrade. Now, if we move on to TFM, using the same probe with an LL waveset, longitudinal and longitudinal, notice the difference first in the near surface, but also that as we go deeper and deeper into the material, the shape of the hole remains much more constant, as well as the amplitude. That's all good and good. Does it have any limitations? Generally speaking, phase array exhibits a better signal-to-noise ratio than TFM, and that is simply because of the wider aperture in phase array produces more ultrasound energy than the individual pulsars in TFM. However, special envelope processing in TFM, other signal process, will help to improve the SNR. In this side-by-side comparison here, we can see the same reflector with phase array and TFM normalized to roughly 80% there. And as you can see, the A-scan background noise is better on the phase array than on the TFM side. Addition of self-tandem waveset to standard pulse echo. Traditional phase array uses pulse echo method, where the same group of elements, or the same aperture basically, pulses and then receives the sound. The self-tandem technique in phase array, although it's less common and often more dedicated to specialized applications such as the pipe wizard, for example, use one aperture to pulse and a different one to receive. One of the advantages of this technique is that it allows for the detection of vertical flaws. TFM uses the same principle when rebuilding the sound path. And just like when it's applied in phase array, the self-tandem technique requires to be more precise when defining the inspection scan plan because of all the geometry that's involved, all the trigonometry that's involved. Parameters like velocity, thickness are very important to get accurately. So aside from vertical flaws that are hard to detect and characterize, such as lack of fusions on ERW welds, the self-tandem technique or waveset also provides better imaging of flaws such as cracks. It's just that the profile of the flaw, as we can see on the very right hand here, is just more true to reality instead of the traditional corner trap and tip diffraction. That can be fairly easy to interpret for experienced users, but may appear as two separate flaws for the beginners. So in the end, TFM just helps to remove that doubt when using the right waveset. Scan plan and modeling. Just like phase array, preparation is key. In phase array, there are some criteria that have to be met to ensure that the inspection results are correct, meaning perpendicular. So amongst them, there's beam perpendicularity to the weld bevel, full volume coverage, adequate coverage also of the heat affected zone. The same principle will apply to FMC and TFM. Detection and characterization capabilities are heavily dependent on the selected waveset, and also the orientation of the flaw and the part geometry are essential to beam modelization when setting the scan plan. So if you do not plan it well enough ahead, you may miss or entirely miss some defects. The advantage of multi-group, for that planning, your inspection may require multiple different wavesets to adequately cover the inspection area. So in this example of an ERW weld, the first flaw was better detected using the Self-Tandem 3T waveset, so detection of the ID over trim here. While if we look at the second flaw, it is better detected with the first leg pulse echo method because it was getting in the hook rack and detecting the corner trap. In this inspection, only 3 groups were required. However, the Omniscan X3 can go up to 4 simultaneous TFM groups. Another important part of a proper scan plan or preparation is selecting the right probe. Same as with phase array, focusing has its limits, which means that what is true in phase array is also true in TFM. Probe frequency, element size, number of elements in the probe, there are all some factors that will have an impact on the setup and the quality of the inspection. If we look at the most right example, a probe with a higher frequency and a bigger pitch will allow for larger sound paths as these parameters increase the near field, hence the focusing ability. On the other hand, the near surface resolution is impacted negatively. So in the end, a good preparation for an inspection should include probe strategy, but also feasibility test on coupons or samples to ensure that the area of interest is covered adequately and returns good signal. 0-degree inspection using TFM instead of phase array linear scan. Why use TFM without a wedge? So in many images that we see, mainly in promo material, we often see probe in contact with the part or the demo block directly. But why is that? There are 3 main reasons explaining this. First of all, this ensures that there will be no wedge echo interfering with the inspection. Number 2, we do not lose any single strength in the wedge, so no wedge attenuation is involved. And number 3, also remember that TFM is focused everywhere, but as long as we stay in the near field of the probe. If we add a wedge, a delay line, it means that part of this near field is now in the wedge and not in the material where we actually want to focus. In this example, we have a small flat bottom hole that is resolved from the background signal using a 10 MHz small pitch probe. Adding a 23 mm Brexolite wedge induces a lot of noise. First, because we had to add 30 dBs of gain to reach the same 80% amplitude. Also, the signal or the flat bottom hole is much less defined. And finally, there's the wedge echo repeat also that's interfering with our inspection. TFM can reveal what's in. So another difference between TFM compared with phased array is that it lets you see what's hidden behind the first indication. We see it a lot with the resolution blocks. We get very nice images of side drill holes. But actually, I'm guilty myself of setting a linear scan with phased array, putting it on this specific block with vertically stacked side drill holes, and just expecting to see all three side drill holes with the resolution getting worse and worse as I go deeper in the material. That's not the case with phased array. I just got too used to using TFM in this. Here are a few examples, application examples of the benefits TFM can bring to zero-degree inspection, starting with HTHA or high temp hydrogen attack, such as early stage HTHA, microfissuring, volumetric defects. So some examples of applications that are either hard to detect or altogether impossible to detect with traditional phased array. So example number 2, some volumetric. Another example is the detection of links between blisters or stepwise cracking. And just like the example with the stacked side drill holes, TFM allows for the detection of not only the blisters, but also the link between them. This can make a huge difference between accept and reject, or in other words, between safety and bursting. Angle beam inspection, comparing phased array sectorial scans with various TFM modes. Can I use TFM with an angle wedge? The answer is yes, of course. At the end of the day, ultrasound is still ultrasound, and we cannot reinvent physics. As omnidirectional as a single element pulse can be, there's always a range of operation where the probe will provide good signal, but outside of this range, the sensitivity, the resolution, and just the overall ability to detect any indications will significantly drop. In this example, we have the same probe on the same samples at the same position. One without a wedge in direct contact with the sample, and on the other side with an angle wedge designed for shear wave inspection. Without a wedge, we're using an LL transmission mode or wave set, and we cannot detect anything in there, just noise. While when using the proper wedge and the proper wave set, it's the indication on the weld bevel is easily resolved. And that just proves that although, yes, FMC and TFM provide great imaging and help to resolve new applications, physics is still physics, and we have to work with it. Now looking at a few signal comparisons between phased array and TFM on 25 millimeter thick welded sample. If we think phased array and sidewall lack of fusions, the best results are provided by the ultrasound coming perpendicular to the flaw, skipping off the bottom and going back directly on the weld bevel. The same logic applies to TFM, and in this case, pulse echo 4T waveset was providing the best results and equivalent results to phased array, in fact. ID cracking. The phased array pulse echo technique works to detect and to characterize crack or crack-like indications by detecting one strong corner trap signal, maybe a few facets, and a tip diffraction. This method, when using a pulse echo waveset, is still valid with TFM, and using again the same indication, we can see that the flaw is equivalent in both cases. We have the corner trap, tip diffraction, corner trap, tip diffraction. Basically, the flaw signature remains the same, but we have more resolution with TFM. The advantage of a self-tandem mode or self-tandem waveset, as I was describing earlier, comes into flaw characterization, where the flaw is actually truer or more accurate compared to what it actually looks like in the part. So comparing phase array pulse echo to a TFM self-tandem mode with 3T, and using or reconstructing based on two different zones, let's call it this way, from the phase array probe. It's true for ID, it's true for OD as well. Again, a comparison between pulse echo phase array on the left and pulse echo TFM on the right. Corner trap, facet, tip, corner trap, facet, facet, and tip. If we switch to self-tandem and 5T instead, we have the same flaw signature or same kind of result as we had on the ID with a 3T. So what advantage or why use pulse echo versus self-tandem? It's a matter of preference and ease of interpretation as well. It can provide better imaging for the non-NDT people, for example. Volumetric defects such as porosities. So why do volumetric defects such as porosities produce a weaker signal when compared to planar defects such as lack of fusions? Basically, there's no straight surface to produce a strong ultrasound reflection. TFM can help to discern such indication from the background noise because it is focused everywhere, but also the reflection from multiple angles can help to reconstruct the signal. As we can see on the left, phase array detection of a porosity, and on the right, TFM with a slightly better SNR. There are a few more examples of comparisons between phase array and TFM, and in these comparisons, all four available TFM groups were used to produce different responses, different signal analysis from different wavesets. So on the left, the phase array with its signal as we're used to see here and there, and on the right, the TFM with the various responses. Another example of phase array and TFM and how they compare, how they complement each other. Phase array 1, 2, TFM, TFM 1, 2, 1, 2. And one more, phase array on the left with very shallow indications, and the equivalent with TFM and how they compare. So I really breezed through this one. As a summary, so to answer the question, is TFM better than phase array? Whether the total focusing method is better than phase array, that really comes to a matter of application and preferences, depending on what type of inspection you're going to tackle, the preference remains an important factor, but also testing and validations beforehand, modeling, scan plan, always. When using phase array in focus mode, so combined with the appropriate good quality probe, good quality wedge, the results can be as good as TFM. But this only applies in the area where the beam is focused. And although imaging and characterization is impressive with TFM, it also can lead to poor or no detection at all if the user do not know which waveset to use for his application. So it's not magic. It requires some preparation as well, some guidelines to follow, but it can help tremendously in terms of imaging. And that concludes this 30-minute talk. Sorry for breezing through it so fast. I received a few questions in the Q&A. Let me see. So one of them is, what about sizing? So you talk about representation, but how can I dimension the indication? Yeah, sizing. Actually, TFM sizing is still under review by the different manufacturers, the different code committees, just the industry in general. So there's no clear answer yet about the guidelines to follow or the methods to adopt. And that's I know, a boring answer. But what I can tell you is that from the test I did so far, the comparisons I did in this presentation, there seems to be a correspondence between phased array and the TFM pulse echo mode when using 6 dB drop method or tip diffraction method as well. Sizing of these indications is very comparable between phased array and TFM. A rapid drop technique, or maybe even diffraction technique, would maybe be more appropriate for self-tandem techniques. But I didn't dig too deep in there. So more testing, more validation is definitely required before coming to a conclusion for this one. So although it's still up for debate, what to use, when, and how to size it, that will be addressed also in the future webinar that we're going to have, I don't remember, maybe next month or so, about FMC and TFM code compliance. So stick around and we'll probably have more answers in there. And yeah, I think that concludes this session. If there's any, there's some other questions that we will address through emails because it will require some more investigation on our side. Greg, all yours.
Thank you, Stefan. And for all the attendees out there, we'll leave the presentation open just for a little bit longer. If you have other questions, continue to type them in. We'll gather them up and go through them afterwards, and your questions will be answered either by email or by phone after the event. On behalf of Olympus, I'd like to thank all the attendees for joining us and Stefan for his expertise and participation in today's event. We hope this material presented was informative and useful. This webinar will be archived on our website at www.olympus-ims.com. I realize that some folks have had trouble connecting or hearing the audio all the way through. The audio seems to have cut out here and there. I'm sure that we've got some bandwidth challenges worldwide when our conditions are proving here, so we can probably expect that to happen a few times. So the full presentation with all the audio will be on our website within a couple of days here. So please check back to www.olympus-ims for the updated webinar file. Everyone who registered for the event will receive a follow-up email with links to the archive presentation. So even if you didn't join us, you're still going to get a link to watch it after the fact. So everyone will be able to see it again. That's going to do it for this morning. Thanks again for your interest and for taking the time to attend this event, and we will see you again next time.